part I will talk about disjunction types. To introduce that topic, I will have to talk about case classes in Scala. This is a feature of Scala that is also present in most other programming languages, but only in Scala they are called case classes. And this can be understood by recalling the tuple. So recall we have tuple types that look like this. Tuple types, such as this one, represents a pair of values, or generally a certain fixed set of values of different types, possibly. Now, in this notation, there are no names associated with these values or with this entire type. And for convenience, we can define names both for the type and for each of the values, each of the parts of the tuple. We can define a name. Now this is convenient to remind ourselves what is the reason we are introducing this tuple, what are the meanings of each part. So here's an example. We can say this is the name of the type, my pair. We could say that, and then we would do this, but this doesn't give us a lot because my pair would not be different from any other tuple of int and string, maybe with very different interpretation. For example, here is a much better way of defining a tuple with names, which in Scala is called a case class, but it's just a tuple with names. We put a name on the tuple itself and on each part. So it's still quite the same as a tuple of double and string, but now it is not confused with other tuples of double and string. So for example, if I have in some other part of my code, I have a tuple of double and string that represents the amount I paid and the name of the person I paid it to. And here it represents my socks. So if I did both of this with a tuple of double and string, then by mistake I could have mixed it up, and instead of using socks, I would have used the amount paid, which would be a total disaster because it will, in the code it looks just like a tuple, so you don't know where it came from, and introducing this type with these names helps to prevent this problem. So once we wrote this line here, this defines a name for the entire tuple type. It defines a new type called mySocks, and it also defines names for the two parts of the tuple. And once I have defined this, I can use this definition later in the code by writing things like this. I introduced here a value of type mySocks, and the value is equal to this. So I can write it like this. And the type annotation here is optional. It is not necessary to write it. Actually, in my code, I usually don't write it because it's already obvious it's of type mySocks. It is a value whose type is named right here, so there's no need to repeat it next to it. So I typed it here for clarity only. Now, case classes can use other case classes as types of their parts. As we have seen before, you could have tuples whose parts are themselves also tuples. So here you can have a definition like this. Bag of socks is representing a certain number of identical sock. So I use this type I defined here by name. So I don't have to say that this is double pair of double string. I just say this is my sock. So I use the type by name. And here I would say val bag equals bag of socks, and then I would say, well, the first part I would have to give, and then the second part. So it's just like a tuple except with name. So I have to say, you see, if you cross this out, if you cross out the names, then it will be just like a tuple with a nested tuple. But in this way, you prevent possible errors. So it will not let you write a tuple here. It says it's the wrong type. So in this way, I define values of these types, which are called case classes. But what they actually mean is named tuples. Once you have defined this, you can access each part by name, and that's also very convenient. Remember that with tuples, you have to access parts of them by index. So this is number 1, this is number 2. So you have to remember which one has which number. And if you want to change this, let's say with socks, I want to also say when I bought them with a date. So I add another field here. So now I have to remember which one is number 1, number 2. With case classes, they're names, so you access by name. You just say bag.socks, which gives you this, and that dot color, which gives you this. So then C will be of type string, and it will have the value white. Now, as before, this type annotation is not necessary. Now, another convenience that Scala provides with its case classes is that the parts of case classes can be specified in any order, as long as you use names. If you don't use names, you have to do it in this order. Otherwise, you can do it in any order. So if you say the name. So here is an example where I define my socks, first specifying the color and then the size. Final convenience is that I can specify default values for parts. And then for example, by default, all my shirts are blue. And by default, none of them have holes. So I define this case class shirt with 2 parts, which is string and boolean. And the first part is called color, and the second is called has holes. And I specify default values for both. So when I generate values of this, I don't have to specify all fields. I can just specify some of them, and the other fields will be generated automatically using the default values. So these are just the features of Scala that make tuples more convenient. And this is the first time I mentioned case classes. However, not the last time. So here's a comparison of tuples and case classes in a more systematic way. So actually in Scala, tuples are just syntax for this kind of type with 2 type parameters, and this is actually like a case class. So I will give you this table to look at. So on the left are tuples, on the right there are case classes that have the same values inside, the same types of values inside, but with names. And there are different types, so you could not, in the same program, you could not put this instead of that, or vice versa. It's just impossible, it won't compile. So case classes are safe in this sense. A case class that has no parts exists too. It's called a case object, which is useful in certain cases. So tuples with 1 element or tuples with 0 element exist in Scala. A tuple with 0 element is not called tuple 0, it's called unit. Tuple with 1 element looks like this. It's called tuple 1. tuple with two elements looks like this is called tuple 2. Certainly, I don't yet know why I would use this. Maybe there are some situations when this is helpful, but I just wanted to call your attention to the system here. So everything is systematic. So you can have tuples with 0 elements, tuples with 1 element, tuple with 2 elements, and so on. And corresponding to that, if you want to put names of these tuples, what do? Well, you put names. So for a tuple with 0 elements, you put a name on it, which is this. And that's called a case object. So these are keywords of Scala that you need to use if you want to put a name on an empty tuple. If you want to put a name on a tuple with 1 element, that's what you do. It's a case class with 1 part. And this is already quite useful. You distinguish this from other kinds of values. And this is a case class with 2 parts. So case classes can have also type parameters as type. So type parameters on a case class means that for each value of this type variable, which could be any type, like integer or boolean, string, or any other case class or anything, function, it can be any type. For any of these values of a type variable A and values of type variable B, you have a tuple with names, and the names are here left, right, and count. And the first part is of type A, and the second is of type B, and the third is of type int. So the third type is always the same, but the first and the second types could be different. Whenever you use this case class, you can use it with different types. And so, obviously, you could define the tuple types like this, like tuple 2 with 2 type parameters and names _1 and _2. And then the syntax would be value dot _1, that will give you the first value. And this value dot _2 will give you the second value, which is just like this syntax. So you say value dot name, and that gives you the part of the tuple. And so here you'll do the same. So this is the syntax we saw before, which will take parts of a tuple, but this is a system. So this could be considered as a case class defined like this. So for case classes, there is another major convenience, which is this pattern matching syntax. So before we have seen pattern matching syntax for tuples. A very similar one exists for case classes. You just specify the name of the case class, and that's otherwise the same syntax as with tuples. So again, if you cross out the names, then you have the same syntax as we had before when we did pattern matching on tuples. So there are 2 cases where Scala will do pattern matching. One is the value assignment, val, and then you can do a pattern and then equals something. The second is the partial function, where you have the case expression. On the left-hand side of a case expression is a pattern. So here are some examples. So, for example, let's say A is my socks. And then I want to get both the size and the color of my socks. So I can write a definition like this, where I define x and y at the same time using the pattern matching. So before you could do this with tuples as well, and then you don't specify the name because tuples have no names in this syntax. But case classes can be understood as named tuples, so then you specify the name. And if A is anything else not of this type, then this won't compile. This won't compile. And the second example is a partial function. So suppose we define this function f, which goes from bag of socks to integer, and computes doesn't matter what. Let's say total price for, no, not total price. Let's say I don't know. Total price we cannot compute because I didn't have any prices in my data, but if I had them, then I could compute something. So imagine we have this function that computes something useful, and then how do we define this function? Well, we need some kind of match. So we need to get values out of socks. So one way would be to just do the access by name. Another way is to define it by pattern matching. Then you define all names at once, and this is convenient. And this is another syntax where you define functions on case class with an argument written on the left. See, there are these alternative syntax. You can write it like this, or you can write it like this. And then there's this syntax b match, and then you write as if partial function. Make sure you realize that these s, c, and z are new variables that are defined only in this scope. They're not defined outside of this block. So these are called pattern variables, and the case expression introduces on the left-hand side new pattern variables that are not the same as anything you had before. So remember the shadowing of pattern variables. If here I have value a, I already defined, I could here have also a as pattern variable. It will be a completely different variable of different type, just by coincidence called a inside this scope only. So it is a good style not to confuse these names and use different names. But even if you use the same names here and here, it will still work. This variable will only exist in this scope, and that variable will be inaccessible. It will be shadowed. So now let's look at disjunction types. The motivation for having disjunction types is that sometimes we have situations when data comes in different shapes, and it can be several different data in one kind of container. So for example, if you are asking what are the roots of a quadratic equation, then the answer is it could have two roots, or it could have one root, which means two coincident roots. And if you're asking for real roots, then it could have no real roots. So if we're interested in real roots, then there are three cases. And it's convenient if we can introduce a type that means the roots of the real roots of quadratic equation, and inside this type we have this distinction, but outside it's just one type, so that it's easier to write expressions with it, functions, and so on. Another example, suppose you run a binary search and look for a value. Now you might find the value, or you might not find it. So it is convenient if you could return something that could be a value and an index, or absence of value and index. It would be convenient if you could return this as some kind of type. Another example is you can have computations that may generate an error and fail to make any value, fail to return a value, or they can return a value. And the error could be different, so you want to have a message about what error occurred. So then it's convenient to return a type which is either a value or an error. So it's kind of a either-or situation, or a disjunction in the mathematical language. Another example is the computer games. In computer games, usually you have states that can be different. For example, you can be in some room of different kind, and different kinds of rooms have different properties. For example, a room could be dangerous or not, or have a lot of stuff, or have some adversaries, and you want to represent all different kinds of rooms, all different kinds of players uniformly, so that you don't worry about the values that you have to store. And each kind of room or each kind of player could have different sets of properties. So, for example, a player who is an adversary, or a player who is just static and gives you information but otherwise doesn't participate in anything. These have different sets of properties, and so it would be good to say this is a player. So this introduce a type which is a player, and then a player would be either one kind of player or another kind of player. So mathematically, you want to present, say, for a quadratic equation, you would say it's a pair of complex numbers, or is a complex number. Well, in this case, I wanted to do real, not complex. Because with complex, you always have at least one. You cannot have empty. Well, actually, you could have empty if your quadratic equation is degenerate. For example, 0 times x equals 1. That has no solutions. And you could, 0 times x squared plus 0 times x plus 1 equals 0. That has no solution. So you could have that situation too. Then, in the example of binary search, you want to find a value and an index. So you return a pair. Or you found nothing, so you return empty. So empty tuple. Now, of course, now you see it's not nice that I return just int. I have no idea which one is which. So it would be helpful if I put names on them. So I put names on each part. So this would be found value, and this would be found index or something. I could do that with a case class, as I just showed. In the third example is a computation that gives you either a value or a string. And the fourth example is basically a case class, so each room or player would be represented by a case class with many properties, but different kinds of players or rooms will have different sets of properties. So you want to have a number of case classes together in a disjunction, basically. Either one case class or another case class or the third case class. That's what you want. That's the kind of type you want. So that's the disjunction type. They are available in Scala, and they represent this kind of situations as types. Let us look a little at the mathematical point of view. Usually, the type means mathematically that the function has an argument, let's say f of x has an argument x. The type of x, let's say x is a real number, then the type of x represents the domain of the function. So now we would like to represent disjoint domains. So for example, x is either a point on a line or it's a point on a surface, completely different surface from a line. And so in mathematics this is not often used, but in functional programming it is used quite a lot, because it appears that real-life situations and tasks require a lot of this kind of disjoint domains. I just gave you examples on the previous slide. So how would we do a disjoint domain between line and surface? Let's say line is the real numbers and surface is R2, the real plane. So in functional programming, the way it's done is that the domains are labeled. So we introduce some fixed special set of symbols, which are the labels, like left and right, let's say. These are just symbols that come from a fixed set of symbols. And then we first make two sets. The first set will be a set of pairs, where the first element of the pair is the symbol left, and the second element of the pair is some real number. So this set is the set of all such pairs, and this set is a set of all different pairs where the first element is the symbol right, and the second element is some point from a surface, from R2. And then we make a union of these two sets. Now this is a labeled union because each set has this label, and so there's no way that even if this were R and this were also R, there will be no way to confuse an element from the left part of the union and the element from the right part of the union. And so the disjoint union is always an exclusive OR. It's never inclusive OR. It couldn't be both from here and from here because the symbols are different. So given any such X from this set, from this entire set, we can always determine by looking at the first element of the pair from which side it comes. And we therefore can obtain and know what is the type of the corresponding other value in each case. So there's no confusion if we label the two parts of the union. Even if all these types were the same, if this were R, this were also R, will still be no confusion. Whereas a ordinary mathematical union, you would be confused. You would think, well, R union R is just R. So, but disjoint union is labeled and allows you to always know from which part you come, from which part the value comes. So in Scala, this kind of type, this disjoint union or exclusive OR between the two domains, is denoted like this. So it's a special library defined, a special type defined in the library called either. It has two type parameters describing the two domains. The first, let's say double, that's describing this. And second is a tuple of two doubles, which describes this. So this was a very close analogy with a mathematical disjunction between the two domains. And as I just said, domains in mathematics corresponds to types of variables in programming, in functions. So types of variables is exactly the same as a set from which the variable comes. So like x comes from the set of real numbers. And here double is a type that approximately represents real numbers. And pattern matching is used to define expressions with such types. So let's look at examples with either. So we were looking before at the situation when we wanted to generate error messages with computation. And so let's suppose we have a function that needs to return an integer but may actually have an error. And so it returns this type, either of string and integer, which is a disjunction between two domains. The first is the set of all strings, the second is the set of all integers. And it is labeled by symbols left and right. And these symbols also come from the Scala standard library. Now, if we have a function, let's say log error, we want to write this function that takes an argument of this type. How can we construct an expression using this type? And here's how. We say xmatch, this is a keyword match. So say xmatch, and then you write this partial function which matches against possible values of x. And there are two cases. Left having an error value, which is of type string, and right having a result value, which is of type integer. In both cases, we can specify what needs to be done, or rather the expression that needs to be computed. Well, we can print, of course, but we need to return a value, and this function must return integer value. So let's return some integer value, why not? And then the result. This is just an example. Now, how can we interpret this code? What does it mean? Case left error, case right result. It means these are actually possible values of this type. So this and this are specific possible values of this type. Remember that we had this labeled disjunction. So this is a possible value with symbol left and a number. And so similarly here, a symbol left, which is the name of the case class, but this is just a symbol. It is not itself a value. It does not give you a value until you give it this, the string. And so left of blah is actually a value of type either string int. And similarly, right of 1, 2, 3 is also a possible value of this type. So in this code, we enumerate the possible cases, the disjunction. There are only two cases in this disjunction, the left and the right. And so we enumerate them. And each time we have a pattern variable of a different type. Because if we are in the left case of disjunction, then the error is of string type. This pattern variable, we could have called it x or y or whatever. It's just a pattern variable, and it's introduced right here, and it only is visible within the scope of this expression. So here we cannot have access to error if we want to here. If I cannot make a mistake and try to access this error value when actually I'm in the right disjunction, in the second part of the disjunction, because the error is not defined in the scope that I am just showing in this scope. Only the res is defined. So these case expressions have limited scope. So this expression from the first case until the second, it is one scope. And within this scope, the error variable is defined. Outside it is not defined. And similarly for this. So if we call this function on a value such as right 123, then this function will match. The first case will not match. So then the second case will match. And the result will be returned. So this will be the value it returns. The match is performed line by line. So if the first line that matches gives you this expression, and that's it. No further lines are evaluated. So log error of left bad result will match this because it matches the symbol, the left. And then error will be the variable equal to, the value of it will be equal to bad result. And so it will print got error bad result, and then it will return -1. So case expressions that choose among possible values of a given type when this type is a disjunction. And here is another way of using case expressions with types that don't look like a disjunction, like int, where you say if, so I say x, which is an argument of this function, x match, and then I enumerate certain cases, 0, 1, and then all other cases. So if 0 does not match, if 1 does not match, then this line will be evaluated, and then this pattern matches everything, it's just a variable. So this res will be equal to this x, since we matched it, and so then the same x will be returned. So you could think about integers as a type that has different values like 0, 1, and others. They're possible values of this type. And so you could use case expression also for those. So case expression is not limited to disjunction types or case classes. Integer is not defined as a disjunction type because it has no parts of disjunction, but it has different values. And so just to note the similarity between this code and this code, the case expressions in the partial function enumerate possible values of the function. And so here also, I'm not limited to just writing two case lines here. Case left error, case right res. I could write anything I want, like for example, case left and then empty string instead of error here. And that will only match when x has that value, left of empty string. Then on the next line, I could say case left of something else, and will match only when x is that. This is just to let you know that the case expressions are more powerful than just matching the two parts of a disjunction. They are matching anything. These patterns can have many conditions, and this can be complicated. So either is an example of disjunction, but there are more general disjunctions. Like for example, what if I want to have a disjunction between three different domains? Do I have to do either of either? So that is not convenient. Now, in principle, what I want is something like this. I want to just say this type or this type, or let's say this type or this type or this type. This is a disjunction. I want to be able to define disjunctions like this. But Scala does not have this syntax. There are some libraries, like these libraries, that provide syntax similar to this one, but I don't want to go into these libraries. They are more advanced. Right now, I want to use the standard syntax in Scala, which is sufficient for most purposes in the more ordinary applications of functional programming, which is most of its applications today. Later I will talk about those libraries and see what they offer, but for now let's use the long syntax, which is available in Scala. And this is the syntax, okay? This is quite long to represent what I would ideally write like this. If I compare this with that, my type is the name of the type. The type has disjunction of three domains. The first domain is a list of integers. So the first domain here has a name. All domains must have a name in a disjunction. It's a label. So here in this syntax the name would be implicit, something like _1 or something. But in this syntax, in the long syntax, the domain has to be explicit. So the name is have_list_int. It has one part, so it's a tuple of 1 with name have_list_int, and the part is named x, let's say. Then I have to write this keyword, extend my type. And in this way I say that this case class is part of a disjunction, which I'm going to define now. So my type is the name of the entire disjunction, and these are the names of its three parts, the labels, and these are the names of the tuple parts. So each domain is a tuple with names. Case class, as I explained, is a tuple with names. So this disjunction has to list the names for everything, for every part of the disjunction and for every part of each tuple. Finally, these keywords, sealed, final, case class, trait, these keywords are necessary in Scala. And what they do is they make sure that you cannot by mistake change this disjunction later, because that would be a difficult bug, that some other part of the program changes this disjunction and then adds some more stuff to it, let's say some other domain, and then your case matches stop working because you don't know that somebody added domains. You have your case case expressions like this, pattern matching, and you expect 3 domains in your disjunction, so you write it like this. But somebody adds a different domain and this stops working. This will crash if that happens. So to prevent that, you say that my trait, called my type, is sealed. So only the ones, the domains of the disjunction that are listed next to it in the file, well, not necessarily next to it, but in the same file, only those exist, and no others may be defined later at any time. Similarly, the case classes are final, so they cannot be extended later. As a result, the syntax is quite long. You have to write a lot of stuff just to express this kind of disjunction of 3 domains. But you write it only once, and using it is quite short, is not so bad at all. So, for example, first I create a value of this type. So this could be a result of some computation with conditions. If some condition holds, then the value is have_socks with some socks values. And otherwise, it's have_list_int with some list_int value. So this is computed, and then later somebody wants to find out what that x was, and they don't know. This could be in a different part of the code, and this could be even in a different library, and so you have to match on the 3 domains of the disjunction. And that's how you write it. You put pattern variables in the case classes. So these names don't have to be the same as these. They can be for convenience, but they don't have to be. I'm just specifically selecting all different names just to show you that these are arbitrary names. They don't have to be the same. And then you write expressions here that will be evaluated in each of these cases. And this expression, for example, is allowed to use this LST, but not this and not that, because the scope is limited. So the scope of definition of this LST is only this expression. The scope of definition of P and Q is only this expression. If you try to use P and Q here, the compiler would say cannot find symbol or something like that. A very often used disjunction type is called option. Here's how I would implement option in a very simple way. It has a disjunction of two domains. One domain is a tuple with one element of type T, where T is a type parameter. And the second domain is a tuple of 0 elements, or unit type, which is represented as a case object. This is just a keyword in Scala. It doesn't really mean anything different from a tuple with no elements or a unit type. And notice here it extends option with type parameter nothing. Nothing is a special type that has no values at all. So this is used to signal that this is an empty tuple. It does not have any values inside. So we cannot use any type for parameter here, but we must specify a parameter. So we use this special type nothing. All of this is defined in the standard library of Scala. Then nothing, option, sum, none. So sum and none are the two labels on the two domains of the disjunction. Now, in order to use it, you do pattern match, for instance, like this. Here's a function that performs safe divide. Divides x by y, but returns an option of double. And so option is a disjunction, and option parameterized by the type double is a disjunction of either a double or nothing. So no value, or rather unit is a type, or empty tuple, if you prefer, is a type that does not carry any value of type double in it. And so here's how you define a function that computes this. It checks the condition, and if y is 0, you return none, which is this label. Otherwise, you return the value x divided by y, labeled by the name, the symbol sum. Now the symbol is a label on the second part, or here on the first part of the disjunction. And here's how I would use it. So I would say safe divide 1 divided by q. Maybe q is 0, maybe not. But I then match. So this returns an option of double. I match the option with two cases, sum x and none. So these are the two parts of the disjunction, and I match on them. And so if I have sum x, then I multiply that sum, whatever previous result, by that x. And otherwise, I return previous result. So this is a kind of a default value that I return when I don't get anything out of this function. And this function returns none, which is a valid result of type option double. Many Scala library functions return an option type, such as find returns. So find looks in a collection and returns an option. If it found, then it returns sum of the value, and if it did not find, it returns none. Head option is the first element of a collection, but if it's an empty sequence, there is no head element, no first element, so it returns none. Otherwise, it returns sum with the value of the first element. And similarly, these library functions, which you can look up in the library or in IntelliJ. These functions return option. And the final note is that option has many functions or methods defined on it. In a sense, option is like a collection. It's like sequence of t. So option of t is very much like sequence of t in terms of what you can do with it. You can, you see, with sequence you cannot do this match because sequence is not a disjunction between none and some. But sequence has map, flat map, filter, exists, and so on. All of this is also defined on an option. And you can understand this in a simple way if you imagine that a sequence is like a container and the sequence of t is like a container where, or let's say array of t is another kind of sequence, is like a container where you have 0 or more elements of type t. So this container holds values of type t. It can hold no values, empty array or empty sequence, or it could hold 1 value or 2 values, and so on. Option is like a container that can only hold 0 or 1 values of this type t. It cannot hold 2. So it's like a very limited sequence, a sequence that can only be of length 0 or 1. Otherwise, it looks like a sequence. So it has a map function, flat map, filter, and so on. So what, for example, what's a map on an option? I will show you when we go through the worked examples how that works. Map on a collection, let's say on an array of integers, you can do a map with a function that maps integers to strings, say, in some way, and then you map and you get an array of strings where each element is transformed by that function. Option will behave in a very similar way. You do a map on an option, and every element in an option will be transformed using the function you specify. However, option can only contain at most one element. So it can be empty, which is this disjunction part, or it can be non-empty, containing one element of type t, one value of type t. So it's kind of a very limited, simple-minded collection, but otherwise it's similar to collection. We will see how that works in the examples. So with the tools we just learned, what problems can we solve? We can represent values from disjoint sets or domains as a single type, and we can use these values to define functions on them or functions producing them, and use also these values in collections as elements of collections, or in any other way. These are types, so there's no restriction on how you can use them. So let's go through some examples now. The first example is to define a disjunction type, day of week, that represents the 7 days of the week. Let me go to this example. So here's what it would look like. So all these keywords here in IntelliJ you see in bold blue, dark blue: sealed trait, final case object, extends. So these are keywords of Scala. And everything else is our labels that we introduced. So day of week is the name of this entire type, the entire disjunction type. It has 7 domains, and these domains don't carry any values, so these are just empty tuples. And the syntax for them is to say case object, and then you don't write this. This is a mistake. You should not write that. Empty tuple is written like this, indeed. But you don't have to write it here. So the syntax is such that you don't write it there. So when you put a name on an empty tuple, then it's called a case object, and then you don't write parentheses. So here's how we define the type. How will we use the type? Like this. We'll define values a and b, let's say, of this type, and assign these values. So we define Monday and Saturday just like this. We don't have to do anything else. We don't have to say new Monday. There's no new Monday. There's only one Monday, because it's a label of the domain in a disjunction. There's no sense in it to say new Monday. You cannot have different Mondays. They're all the same. It's a label on the disjunction. Now, if I don't do this and just say val a equals Monday, then Scala will actually not know that I want a to be of this type. Scala will think that it has type Monday type. So Monday.type is a Scala feature that I'm not going to use right now. It is a more advanced feature. So with these disjunction types, it is a good idea to write type annotations. Scala can be too smart about what I want to do, and so it is better if I do this. But it would not be an error if I did it that way, if I put just a without type annotation. Probably my code will still work. It's just some types will become weird. Now, suppose I want to print. Now, how do I print this? Well, actually, case classes and case objects already have a toString method defined on them. So I can just print like this with string interpolation. And this will run, and I will get this string printed after we implement the function so that this test can pass. So how do we implement this function? This function is supposed to give us a boolean, which is true when the day of the week is Saturday and false otherwise. So we do this by pattern matching, since the type is a disjunction. So we need to match on the label of the disjunction, or in the Scala language, we match on the case class or case object. So we say dmatch, and then you see there's this red, case closes expected, sure. And then there's this thing, which I can click, and it says generate case clauses for variants of sealed type. Now in the Scala language, this means this was a sealed trait that I defined, and it has 7 variants, or disjoint domains in my understanding. And so if I click this, IntelliJ will fill in the code. Actually, I'm not sure why it's doing it like this, because it's from another example. I guess it's a bit confused, but it allowed me to delete what was not necessary. So it generated most of the code. So now I need to put the expressions that I'm going to return in each case. So if this day is Saturday, I need to return true. Otherwise, I need to return false. Now there's a lot of, I could say false, false, a lot of work like this. So I'm going to be more clever, and I'm going to do this. I'm going to put Saturday first, and then if there's anything else, I'm going to return false. So let's say like this. So in this way, I'm expressing my intention much more clearly. So Saturday, true. Otherwise, anything else false. So there's one little thing. So this will work. We can run this test, and this will work. There's one little detail here. So green. Notice what it printed. A is Monday, B is Saturday. So this is the string that I printed here with interpolation. So A was Monday, and it's already printable. So this is a convenience that Scala gives. Now, the little detail I was talking about is that IntelliJ says declaration is never used. So I declared a variable x, but I never actually used it. There's a syntax which looks like this. Needs to be used in this case to make it more clear. Like I said, this still works. This is not a mistake to do a variable that you don't, to use a variable here and never actually include it anywhere. So to left it unused. It's not a mistake, but it is a little misleading because you're introducing a variable, and so I'm looking for its use, maybe. I don't find one. So this syntax means it's a variable that matches anything, just like x. No conditions on it. Variable matches anything, and I don't need its name. I'm not going to use that variable. So the underscore in this situation means that it's a pattern variable that I'm not going to use, so I don't need its name, and it matches everything. And my tests are that A and B, so A was Monday, B was Saturday, they pass. Let's go to the second example. Modify day of week so that the values additionally represent a restaurant name and total amount for Fridays and a wake-up time on Saturdays. So what does it mean? I want additional values on these disjunction, on the domains in the disjunction. I want these domains to be not just empty tuples as I did before here, but for Friday I want a domain that represents a string, which is restaurant name, and an amount paid. So here's what I do. I make Friday and Saturday case classes instead of case objects. And then I'm free to add parts in there with different types. So field called restaurant name, type string, and so on. So I can do that. And similarly for Saturday. Now I think I haven't finished this, so this is supposed to be wake up time. So I think I want to do a local date time from the java.time library, and that's a wake up time. So this is it. So basically I have easily added more data, but only for these 2 days. So these days still have no data. So if the day of the week is Monday, then I didn't go to restaurant and I didn't pay anything, and so on. So now let's define some test data. Day of week is Monday. Now if I want to define Friday as day of week, then I have to specify the parts of this case class, or the fields with names. Now here's what I do. I say like this, and now I have defined the value of type day of week. I still print it, and then I want to define a function that will tell me how much I paid on a given day of the week. Now notice, on most days I didn't pay anything. Only on Friday I pay, because I go out. So this function will return an option double, and this option will be none, or empty option, for all the days except Friday, because there's nothing to be paid. And on Friday, I will return this amount. Notice this is cleaner than returning 0 for other days. I could return just double here instead of option double, and I could have substituted 0 on those days. But this is cleaner. What if somehow the amount paid was 0 for some reason? Let's say I went to a restaurant and I had a coupon and I didn't have to pay anything. I was free. So my amount paid was actually 0. But I did go to a restaurant, so that information is not lost if I'm returning option double. And if I give Friday as day of the week, I will get a non-empty option with a value of type double inside it, and that value could be 0 or anything else. I don't use any special values to denote the absence of amount paid. The type denotes it, the option type. That's why it's so useful. That's why it's used so much in the library. Let's implement this function. Again, we do a D match. And again, I'm going to fill in. Let's see what it tells me. Oh, great. This is because I have two different case classes and case objects and traits defined with the same name in the same file. So IntelliJ is a bit confused. I have defined them in the scope of this test, so they are completely safe and invisible in the other test. But IntelliJ is not able to see that. Okay, I'm just going to correct this by hand. Not a lot of work. All right, and Friday and Saturday are actually correct now. All right, so now if I'm on Friday case, then I need to return sum amount paid. So sum is the constructor for the domain of option that is not empty. So I call this a constructor because this looks like I'm calling a function, which is called sum, on a value. So it's like a constructor. The word constructor will be used quite frequently. There's a type constructor and there's a value constructor. But let's talk about how to implement this function now. We'll discuss the constructors later. All right, so in all other cases, I have to return none. So I have to return none here, here. Okay, I'm bored. I don't want to write all this code, so I say first case is return this, and in every other case, I don't know what that is. I don't need to know. I return none. This is how I would write it. And also here, this declaration is never used. I'm going to put underscore. So now this is how I would write the code. Also, I like this symbol to be nicer. So I have a special IntelliJ shortcut to insert this symbol. And this symbol is exactly the same as this combination. So there's no difference. It's just pure aesthetics. I like this symbol. This is the way to write this kind of code. And it clearly says, here's a disjunctive domain, which we match and specify different possibilities. One possibility is that it's a Friday. So a subdomain of the disjunction that is labeled as Friday with these two values in it, and then I return that. Otherwise, for any other domain, I return none. So let's run this test and see what it prints, because we printed here Monday and Friday. Right, so here's what it prints. Interesting. A is Monday. B is Friday of McDonald's and 23.49. So this is the way Scala prints case classes. This is the default way to print case classes. So you don't have to write code for your own printing function or toString function. The function toString is already defined in a reasonable way. It may not be what you want to print to your users, but for debugging, this is pretty good. Let us continue. The next example is to define a disjunction type, roots of quadratic, that represents real valued roots of the equation x squared plus bx plus c equals 0 for arbitrary real b and c. And there are three cases: no real roots, two real equal roots, two unequal real roots. Notice I make this quadratic equation non-degenerate so that it always has the term x squared. If I said ax squared plus bx plus c, there could be a case when a is 0, and then we'll have a linear equation. So in this particular example, I chose it to be like this for simplicity. And then we want to implement the solve function, solve2 or solve quadratic, which takes a tuple of two coefficients, b and c, and returns this value of this disjunction type, which is a roots, whatever situation it is, it returns that value. And that value represents a disjunction of these three cases: no real roots, two equal roots, two unequal roots. And conceptually, this is easy to think about. You call this function, you get the value, and then you can match on it and see what the situation is if you feel like it. How do we implement that? Let's take a look. So I define sealed trait, roots of quadratic, final case object, no real roots, extends roots of quadratic. So I say again, all this final extends and sealed traits, these are Scala keywords. This is kind of verbose, but you just only write this once for every disjunction, and you never look at this more than once. So that's, to me, that's acceptable, although I would prefer, for example, that everything is sealed by default and everything, excuse me, everything is final by default. I would prefer that I don't have to say final all the time, but it's okay. It's not so bad. For the value it gives us is that we can represent arbitrary disjunctions of types like this, case classes and other types. So there are three domains in the disjunction, as we were told. No real roots, and that has no values, obviously, no roots. So we say this is an empty tuple, and that is represented by a case object. Yeah, also this case object, that doesn't have to be a new keyword in principle. So, but that's what Scala requires. Just remember that this needs to be written like that. Second domain is when the roots are equal, then there's only one number to store, and that number is x. And so the third domain is when there are two unequal roots, and then there are two numbers to store. Alright, so we have defined the disjunction type, and now we define a function, solve2, that takes a tuple of its coefficients, a, b, and c, and returns roots of quadratic. So how does it work? Well, we say, I chose this syntax just to be a little on the pure side of things. You know, value, I could say this is a val. Functions are values, right? So I could say this is a val. Since I don't have any type parameters here, I can do a val. If I had type parameters, I would need to do a def. All right, as I say here, okay, so there's a val. The function takes a tuple of double as its argument. So to define this function, we say case BC. So we do a case because this is the way to use tuples as arguments in Scala. So this is the syntax. If I don't say case, not sure it will be happy. So you see, this function has only one argument. This argument has type tuple of double, and so that's why I need to do a match on that one argument. So I already need a match right here. Okay, so here's what I do. My b and c are these two coefficients. So I determine the discriminant. And if it's greater than 0, then I have two different roots, which are given by this well-known formula. And then, so I just, for clarity, I define names x1 and x2 temporarily, and return two roots, x1, x2. Here, if discriminant is 0, I don't need to define any names temporarily. It's too easy to say just equal roots of minus b over 2. In here, I could also put these two expressions directly into the constructor of two roots case class, but this is more clearer in this way. Finally, if the discriminant is negative, there are no real roots. So in this way, I return a value of this type. I construct this value as an element of one of the three possible domains, each domain having its own values in there. So this is a disjunction of empty tuple, tuple of 1, and tuple of 2. But I put names on them, so now it's much more readable. It's clear what I'm doing and easy to check for mistakes. So let's now check that this works. So here's what I do. I define a sequence of tuples just so that I can check at once all these equations. So this is the equation x squared minus 2x plus 1 equals 0. So this equation has a double root, x equal 1, obviously. Now this equation is x squared plus x plus 1 equals 0. And it has no real roots. Its roots are complex. This equation is x squared minus x minus 2 equals 0. It has two real roots, two different real roots. So in this way, I check all three possible domains and all three possible cases. And so I have a sequence of these three tuples, and I map over this sequence with the function solve2, which takes a tuple and returns roots of quadratic. The result is a sequence of roots of quadratic. So then I check that the sequence is equal to what I expect. The first one has roots, only one root, x equals 1. The second one has no real roots. The third one has two different real roots. So that test passes, and it shows that we have implemented our function correctly. Now notice that this function returns a value. It doesn't bail out or generate errors. It always returns a value. This value has 3 different domains. In some domain, there's no result. In another domain, there's some result. So this is the way to deal with complicated logic and complicated domains in functional programming. You model this domain with types. So you make a type that represents everything you want to say as much as possible, and then you write code with it. So you see, it's quite easy to write code with this. There are no special values. There's no flag, Boolean flag that will be true or false when you have roots or you don't have roots. You don't do any of this. It's much more visual and clear when your code exactly says what's happening. There are no hidden flags, hidden special values. This is the advantage of using disjunction types. Actually, this is one of the main advantages over using some other methods of representing complicated data. Next example is that we want to define a function called root average, which is from roots of quadratic into option double, that computes the average value of all real roots, returning none if the average is undefined. So it means if there's no roots, then we return none. Otherwise, we return the average of the roots. So how do we implement this? The test is already written. So for example, root average of this should be 0, sum 0. So it's option, right? So non-empty option has the form sum 0. Empty option has the form none. So these are the 2 domains of the option. And so you always have to write the sum and this none. This is a bit verbose if you have a lot of those values, but you need to think about how to reduce the verbosity, but you always have to write specific values like this. If you have equal roots, then average is the same as this one value. Otherwise, you get none. So how do you implement? Well, you say roots match, and then you say generate case clauses. I'm just lazy. And then clearly, if we are in this domain, then it's none. Here it is sum x. Here it is sum of x plus y divided by 2. That's it, we're done. No way to make a mistake. You see, no Boolean flags to check, nothing. No way to make a mistake. Very safe code. Finally, what do we do now? We generate 100 random coefficients b and c and compute the mean of root average for all of them. Let's do that. So first we make a function getRandom that generates a random number. So let's say between -1 and 1, we generate uniformly distributed random numbers for simplicity. And we prepare a sequence of coefficients by filling 100 random numbers. Now each getRandom will be a new number. It is actually good style in Scala to make these functions syntactically different from values, so that you see that this function actually computes something new every time. It's not just a value, because I could call this random. I could rename it. And then if I don't write these parentheses, then it looks like a value. It looks like it's going to be the same every time. But right now it's not. It's a new random number. So to emphasize that, the style convention often in Scala is that you do the empty parentheses, which is kind of a function of 0 arguments, which you can also think of a function of an empty tuple as an argument, but in Scala it's actually different. You have functions with 0 arguments in Scala, which are different from functions of single argument that's an empty tuple. Scala is a bit redundant in this way, and this is because it has to maintain compatibility with Java. But this is never a big problem. So the syntax helps if you use it in a way that is suggestive. So we make these coefficients, we get a sequence of random numbers, and then we map over this sequence with the function solve2 that we implemented just previously. The result will be a sequence of this roots of quadratic that we have. So each element of the sequence could have different configuration of roots, no roots or 1 root or 2 roots. And it's all in this type, because this is a disjunction type. Now we compute averages. So solutions, we map over that sequence with root average. So remember, the function root average takes roots of quadratic and returns option double. So when we map with this function over a sequence of roots of quadratic, we get a sequence of option double, each element being transformed. Now, that's not what we want, though. Now we want to compute average of this sequence, but it's a sequence of option double. So some of them are none, some of them are not none. How do we get all the ones that are not none to take the average of them? So I will show you several attempts to do that. And the first attempt is to filter the averages by retaining those that are not none. So we do this with a filter, with this matching expression, which is actually working, but it still gives you a sequence of option of double. It does not eliminate the option type. And that's kind of bothersome. So there are two ways in which you can do it more easily and more safely. One way is to use this flatten function on sequence. So it's a special case when you have, so flatten, usually what it does is that you get from a sequence of sequences, you get a sequence. So usually, for example, so usually it's sequence of t, and you get from it sequence of t. But also, it works with sequence of option of t, and you get from it sequence of t. So this, usually what flattens do is just, flatten does is just, every sequence here is concatenated and you get one big sequence. Now, if you think that option is like a sequence of at most one element, you can do the same operation. You can concatenate all those options that are not empty, discard those that are empty, and you get a sequence. So that's what flatten does. And that's exactly what we need to do here. We have a sequence of option of double, and we need to discard those that are empty and get a sequence of double as a result. So that's what flatten does. As another way of achieving the same result is to use the collect function. Collect function is quite useful because you can do partial function here and match and transform things and transform types also. So here I transform type. So this is an option type, option of double, and this is double. So I have transformed the type. And the collect function will check that this case actually matches. And empty options, it will not match, and they will be discarded. So that is how these functions work. Very useful functions. In this case, flatten would be my preferred option, my preferred way of implementing it, because it is shorter and very clear. I just want to discard all empty options, and that's what flatten does. But if I have some more complicated transformation, discarding some elements while transforming others, and flatten is only defined for this special case, sequence of option. For example, flatten is not defined for an option of sequence or for some other such things. Then I use collect. So, but anyway, we can run this test now, and either result 1 or result 2 will compute exactly the same thing. Let's see what it prints. Oh yeah, interesting. Some interesting number, average root. Fine, so this is our result. The final worked example for this tutorial is slightly different. So far we have been computing things. Now we want to implement a function with a fully parametric type, which is given like this. What does this function do? It takes a tuple of two options and returns an option of a tuple. Now actually I forgot the double parentheses in this type signature. This must be double parentheses, and in my code I believe it is. Like here. A function that takes a tuple must have double parentheses, because in Scala the syntax is that the first pair of parentheses designates the arguments of the function, so we can have one or more arguments, and each argument could be a tuple or not also. So if you have just one argument that's a tuple, then you must do this double parentheses. So I should have done it here too. I will check, I will correct this in my slides. Let's look at the implementation. So I start with the test. So if I had such a function of type tuple option int option string, let's say, into option of tuple int string, how would I check that this works correctly? For example, if both options are non-empty, then I want to return a non-empty option of the pair. But if just one of them is empty, I cannot return the pair. I cannot have a pair because I don't have the other value. And so I must return none for the entire option of tuple. So this is the only way that this function can work. And this test then checks that this is so. So it returns none in all cases except when both of these options are non-empty. So here's the implementation, one implementation of this function. Let's reason about it to see how this implementation can be derived. Well, first we say these are the two arguments. So let's match on the first argument. The matching of the first argument has, let me delete this perhaps and write the code again by reasoning about what needs to be done. So obviously maybe A is an option of A, so it maybe is an empty option, maybe not empty. So maybe we have an A, maybe not. So we need to match to do the case clauses. I generate them. So then let me call this A just for clarity. Okay, so now I have two cases. either A is non-empty or A is empty. If A is empty, I know what to do. There's nothing else to do except to return empty option of this type. Because if I were to return non-empty option of this type, I would have to supply both A and B. But I don't have B. Sorry, I don't have A. My A option is empty. There's no way for me to get a value of type A because I don't know what that type is. I'm not given a value of type A and I cannot create it from nothing. So I must return none. In case that the option A is non-empty, I have hope that maybe also B is present. So let's see if that is so. Maybe B, I need to match on it. Let me again generate cases. So let's call this value B. All right, so if B is present, then I can actually return A and B in a tuple. So I'm supposed to return an option of tuple. And so I return non-empty option, sum, with tuple as the value. And here I again must return none, because there's no other way. So basically my implementation is more or less fixed. Except that, of course, I could return none here as well, and the type would be still correct. It will be a very uninteresting implementation that always returns none, whatever the arguments. And the only interesting implementation is this one. Now, by interesting, what I mean is it does not discard all the information in the arguments. It discards some information sometimes, but it doesn't always discard everything. So this implementation is non-trivial, and it's the most information preserving one, and therefore the most interesting. Now, this code actually, it is correct. I have tests below that call my check function on F1, so I can check that this is correct. But this is verbose. All this match, case, and then case none goes to none, case none goes to none. All of that is quite verbose, and if I wanted to modify logic here, I would have to modify a lot of things. So remember that option is like sequence. So it has a map function defined on it, map method. I use the word method and function interchangeably, but in Scala there's a difference. Methods are those things defined with this syntax on a class, and functions are values of function type that cannot be used with this syntax. Again, this is a legacy of Java. Java does not have functions at all. It only has methods. So Scala must have methods too, and yet Scala wants to have function values. So this is a compromise. We have both in Scala. We have methods and we have functions. For the purposes of functional programming, methods are just like functions. So I use the words functions and methods interchangeably. It's just that this syntax must be different. If map were a function, not a method, then the syntax would be map of maybe A, F, something like that. And it's exactly similar. Map, logically speaking, has two arguments, maybe A and F, but the syntax is that map is written in between with a dot. And actually there is an alternative syntax like this, without dot and without parentheses. But I don't like that syntax so much. Sometimes I use it, but only when it is really easy to read what's happening. So let me remove this. What I wanted to show is that this code is so common and it's exactly equivalent to this code. If you have this code that matches on an option, so maybe A is option of some type, and you match on it, and if it's not empty, then you return a non-empty option with some transformed value, and if it's empty, you return empty. This is exactly the same as doing a map on a collection. If a collection is empty, you return an empty collection again. And if it's non-empty, then you take each element and you transform it with the function. And then you return a collection having those transformed elements. An option, being a collection with just one element, only needs one such transformation to be performed at most. And so this code is exactly the same as this code. So let's take that code and simplify it. Instead of maybe B match, we just have now, we can write, let me write this as a comment. So this, actually let me copy the entire piece that I'm going to simplify and do it step by step, looking at this template here. So whenever I have this pattern, sum of x going to sum of f of x, none going to none, I just do a map. So I have this pattern right here, maybe B matches like that. So instead of this, I say maybe B dot map, and then the function is from B to the tuple AB. And that takes care of this thing. So now the code is much shorter. It has this shape, and but it still has the same pattern. Match sum to sum, and or to option, none to none. So let's do maybe A dot map, and then A going to this. So the entire code was replaced by this. Does it actually work? So let's go and see what happens with this implementation, which I called F2, where I wrote what we just saw. Maybe A.map, x going to maybe B.map, y going to tuple xy. Exactly what we ended up with here, up to renaming of variables. So let me remove that. Now, actually, it's not quite right, because the type of this thing is option of AB. You see, this type is option. After mapping, we have an option. And then this has a type A. So we map x of type A into an option of something, and the result is going to be option of option. Let me write a comment explaining how this happened. I have option of A, then I do map with a function that goes from A to option of B, or option of tuple AB. And the result is going to be, you see, this A is going to be replaced by this through the map function. So the result is going to be the type option of AB. And that's what IntelliJ tells us. If I delete this, that's what it knows the type is. So we need to transform this to an ordinary option. how do we transform? Well, this is the whole logic here. If both of them are non-empty, only then we get a non-empty option at the end. So that is what flatten does. A collection of empty collections gives you an empty collection after flattening. So we just use flatten and that's it. Now that works. So that's a valid way of doing it, but it's not the best, because there's this pattern which is map followed by flatten. And this pattern also seems to be very, very often used. And so in the standard library, there is a method called flatMap, which is the same as map followed by flatten. And so actually, the code that you could write would be this. Now, it is questionable whether this code is easy to read or easier to read than this. I would actually say this code is a little easier to read because it is map, and here's flat map and map. There are other ways of making this much easier to read and to write, which I'll talk about later. This is the for yield block notation. But for now, it is important to write all of these things by hand, all of the maps, flat maps, and so on, and to follow the types, to see how the types are transformed. IntelliJ sometimes gives you help here. For example, if I press Command and then hover my mouse over symbols, it gives me some information about their types and definitions. So it tells me that, for example, this is an option of B. This is a map that takes a function and returns an option of B. And these types are not always clear here. What is this? A to B, for example. B to B. I'm not sure what A is and what B is. I mean, this is certainly a contrived example of such a function, but A is this type A, B is this type B, but actually this is not the types we're using. We're using option A and so on. So IntelliJ is not always right when you do this on the map, but IntelliJ is right when you do Control-Shift-P on symbols. So that, for example, is always right. Flatten, option B. So to make a long story short, you need to start with code like this and then simplify it and make it shorter, and then gradually you will start thinking in terms of these map, flat map, and so on, so that it is much easier for you to think in terms of transformations on an option, collection, and so on, rather than transformations done on individual elements. And it's very important to follow how types change. So let me try to rewrite this function in a longer fashion here. And this is what you might do initially when you start learning about functional programming. Code like this is very short. It is not very readable. So what you can do is you can say, first of all, you can make these functions multi-line by putting curly braces around them. And then you can introduce intermediate values. For example, val c equals this. And then you return c. It's the same, right? You call this value c, and right away that is your expression. But now you can see what the type it is. So it's option AB. And you do option return, like on the keyboard, to add the type annotation. And so it tells you that this is actually an option of AB. That information is not obvious here when you look at this code, but you can make this easier for you to understand. So first, maybe B has type option of B. You map it like this, and it becomes option of AB. Maybe let's rename this X into A and this Y into B so that it becomes easier to read. And then also here, you're not sure what you're returning, but flatmap tells you. Flatmap takes a function from A to option B and returns option B. Well, actually this is confusing because your B is not their B. So their B here is defined in the standard library somewhere. It's not your B. So the definition of flatmap is this. There's some B here, there's some A here. That's not what you wanted. That's not your B and not your A. So that is a bit confusing. So let's do the same trick here. Val result equals this. Return result. And now let's add a type annotation to this. Okay, so now if you didn't do flatmap, let's remove this type annotation and add it again. I mean, you could do Control-Shift-P to see what it is, or you can just put it into the code to document that you, at this point, you got a value of this type. So these transformations, each of them will change the type of values, and it's nice to see what type it is to check that that's exactly what you want. Now, obviously, we want an option of AB and not an option of AB, so we need to flatten it here. Oops. All right, so now let me see val what that is. And so in this way, you can go step by step within each of these transformations and see what types they generate. And if you have done this enough times, initially it will take time and you will have many steps. And at the end, you will see it becomes easier. So here are some more exercises for you to work with disjunction types, case classes and collections of them, and implement some functions like these also with fully parametric types. And so these functions are usually obvious what is meant. So for example, an option of a pair goes into pair of options. Well, obviously, if this option is empty, then you must return two empty options here. And if this option is not empty, then it makes sense to return two non-empty options in order to maximize information. And similarly here for either. If you have either of A, B, that could be A, and then you can return here a non-empty option of A, but you must return empty option of B, and vice versa, in order to not lose information. And in this example also, if you have either A, either B, C, so for example, you could have A, and then what do you return? Well, you return the left version of either, and the left version of this either with A inside. So in this way, you can always see what kind of value it makes sense to return in order to not lose information. Good luck with these exercises.